Okay, we're going to start with finishing up mass spectroscopy, talking about fragmentation. There will be a homework assignment that I will post today where I'm going to give you some mass spec and ask you to maybe assign a couple of the peaks or several of the peaks in the mass spectrum based on what fragmentation looks like, which is what we're going to talk about. So we went through the basics last time, and I put that online if you want to go back and review it. But basically, the nuts and bolts of what we learned last time in terms of the mass spectrum is that the peak that is farthest to the right is what we call our molecular ion peak or our mass peak. And so it's our M dot plus, it's our radical cation, it's the molecule as it is intact. Then that molecule, once it becomes a radical cation, becomes kind of unstable, and so it begins to break apart. And as it breaks apart, we get these other peaks, which are going to be fragments of different masses. And so in theory, these are the pieces that when you put these pieces together, you get the molecular ion. And the question is, well, how can I interpret those pieces? What do they correspond to? And just basically, if you take, let's say, take something real simple like pentane. Now, once pentane becomes its radical cation, then a carbon-carbon bond will usually break. And in this case, it could be a number of different carbon-carbon bonds that could break. But when we take a radical cation and we break a bond, when we scission or cleave the bond, it'll break in one of two ways. Okay? We have a propyl group here, and I've got an ethyl group. So let me just, for the sake of argument, I'll put the propyl group here in blue, and then I'll put the other one in red, just so that we know, we can kind of keep track of what's what. So when I break that bond, there's two ways for that carbon-carbon bond to break. One piece is going to become a radical, and the other piece is going to become a carbocation. So in this case, if I start with the ethyl group can either be a radical or it could be a carbocation. When I break the radical cation, I'm going to get the two parts of each. One carbocation, one radical part. And then that leaves the propyl part of this as being, so I'll have my propyl part here will be the carbocation, and down here the propyl part would be the radical. So when I scission the bond, when I cleave it, I basically have these two possibilities. So that the molecules can either be, well, the molecules have to be, one's a carbocation, one's a radical. Now, from what we talked about last week, radicals, since they don't have a charge, they can't turn the corner in the mass spectrum. They can't be affected by the magnetic field. And so anything that has just a neutral charge is not going to be something that we observe. So we're not going to observe this radical, and the same thing up here, we're not going to observe the ethyl radical. What we will observe are the carbocations. Since they're a charge, when they move, they can be made to turn the corner, and we'll determine their masses. So if you look at this, the ethyl radical then it's a CH3, CH2 plus. And so its molecular weight would be, well, it's got two carbons at 12 each, and then 5 hydrogens. So its mass would equal 24, and 5 would equal 29. Okay, so in the mass spectrum of pentane, we might see a peak of 29 AMUs. That would correspond to an ethyl carbocation. And then we would also potentially see a propyl group, which would then be a CH3, CH2, now CH2+, and that would have 3 carbons, so it would have 36 plus 3 is 39, 41, 43. So this would have a mass of 43 AFUs. So if we looked at pentane, we would see both a peak at 29 and a peak at 43, corresponding to that bond cleaving in the 2 possible ways. Now sometimes we'll get more of one pair than another. Sometimes we'll get more of one carbocation than another based on the stability of that carbocation. But we don't see the radicals. The radicals are not observed in this case. Okay. So when we start breaking bonds apart, we're going to basically look for the part that's the carbocation. But one part will be a carbocation some of the time, the other part will be the carbocation the other part of the time. Okay, that's how we have to look at the at what's called mass fragmentation. Now you could say, well, couldn't you just break off a methyl group here? Couldn't I come here and just break off a methyl? Well, I could, and my 2 choices would be that I could either form a methyl radical or a methyl carbocation. The methyl carbocation is what I would observe. If I broke this bond, then I would end up with a 1, 2, 3, 4 carbon, the butyl carbocation, or down here I would end up with the butyl radical. Again, I'm not going to observe either of the radicals. I'm only going to observe this and that. And notice that I'm drawing primary carbocations, which in lecture would get you no points, and probably a big red mark, with usually, oh no, a primary carbocation written next to it, for me, depending on the mood I'm in and how much time I have. But in the gas phase, primary carbocations are perfectly fine. They turn out to be stable. And so all these different primary carbocations that we can write in mass spec, but don't write them in lecture. But that's how the breaking of the bond goes. So in this case, I would also potentially see a fragment at 15, and I would see a fragment here that has 4 carbons of 48, and then 48 plus 3, 51, 53, 55, 57. So I would also see a mass of 57 for the N-butyl carbocation. So when we look at our mass spectra then, here's what we see. We see all the different fragmentation patterns. How do we know which bonds that we broke? How do we know what we lost? Well, let's just think about, let's look at nonane here. Nonane weighs 128. This is its M dot plus. How much did it lose to go from 98, or to go from 128 to 99? It lost 29. What did the 29 correspond to? Well, we just saw that it corresponded to an ethyl group, But in this case, the ethyl group that it lost was the ethyl radical. Now, down here, I see a 29 peak, which corresponds to the ethyl carbocation being formed. So when I broke the bond, I formed both. And then what's left over? Well, 99 is left over. So I took an ethyl group and I cut the bond right there to give me an ethyl radical and then the carbocation on the remaining 7 carbons. So I have a primary carbocation on a 7-carbon chain. Well, the 7-carbon chain is 7 times 12, that's 84, plus whatever number of hydrogens that is, gets me to 99. And so we can look at the differences in the masses to figure out what we lost. To get to 85, I lost 14 off of this 99. What did that correspond to? Well, the 85 corresponds to a loss of 43. What did 43 correspond to? A propyl group. And so that 85 corresponds to breaking one of maybe these bonds, losing the propyl group, and then what's remaining weighs 85. And the 57 we saw that a 57 corresponded to the 4-carbon carbocation chain. And a 43 is the loss of the propyl. But when this bond breaks, sometimes we'll get a propyl carbocation, which is this peak, and sometimes we'll get the rest of this as the carbocation, which is the 85. So we can look at these masses and try and say, okay, now what piece are we talking about here? And we can either do it by looking at 85 and saying, well, what in that molecule would add up to 85? Or we can look at it and say, I lost 43. The only way to lose 43 is to lose a propyl group. And then what's left over gives me the 85. So sometimes we go in both directions. We look at the difference, and sometimes we'll just look at the piece and say, oh, well, that's what the piece weighs. Okay. Everybody kind of see what I'm doing? Is that a yes or no? So if we go to methylpentane, now we've got a carbon that's tertiary in this. And notice that when I go from 86 to 71, what did I lose? I lost 15 mass units. Well, what does that mean? That means that I basically broke a carbon-methyl bond. But now which carbon-methyl bond would I break? Would I break this carbon-methyl bond, or this carbon-methyl bond, or that carbon-methyl bond? Which one of those bonds is the most likely to break? Either of those or the bottom one? The one that will, when it breaks, leave what kind of carbocation? Secondary. So if we look at this, let's say that I broke either one of these bonds. These would be A. We'll call these two bonds A, and we'll call breaking that bond B. If I break A, what do I end up with? Well, I end up with a molecule that looks like this with my primary carbocation. Okay, that weighs 71. If I break, so that would be what was resulting from A. If I broke B, then what would I have? Then I'd have the carbocation on the secondary carbon. And so in this case, which breaking is most likely to lead to the mass peak at 71? The secondary carbocation as opposed to the primary one. Now notice the 71 peak's not very big. What is big? 57. Here's my 29 though. What does that tell me? Peak at 29 says somewhere along the line I broke and made an ethyl group. So in this molecule, what's actually most likely to happen is that I'm likely to break, if I rewrite this molecule over here, I'm actually most likely to break this bond. And when I do that, some of the time I'll get an ethyl radical, which will give me the peak at 29. And the other times, I will get this secondary carbocation, which weighs, I break this apart, I get that fragment, and that fragment weighs, well, it's a C4 fragment, so it weighs 57. And so this is the 57 fragment. This is the 71 fragment. And there's two ways to form the 71 fragment, but which is the most likely way? It's probably going to be B as opposed to A. You still kind of see what we're doing? So alkane fragmentation patterns are based just on breaking carbon-carbon bonds. And you have to look at the mass spectrum to see what the most abundant peak is. 57 is the most abundant peak. That means there's a C4. Where did that come from? Well, that came from breaking one of these bonds. And that gives you a 4-carbon secondary carbocation left over, which is pretty stable. So some of the other fragmentation patterns that we can get. For alcohols, alcohols tend to have really, really, really small molecular ions. Sometimes you can't even see them. Because what happens with alcohols is that once you form their radical cation, they tend to really lose water very easily, which means they lose 18 mass units. And it's really difficult to find the mass peak sometime for an alcohol. So for instance, pentanol here, butanol, has a molecular weight of 74. And that doesn't really show up all that much, but if you say you lost 18, the 56 now all of a sudden becomes predominant. And this is a molecule called linalool that we'll work with later on in the semester. It has a molecular weight of 154, and you can see that the 154 loses 18 to form 136. In this particular case, it'll lose water very easily, and off a tertiary alcohol, it's really difficult to get a mass peak. Now you could say, well, how do you even know then that this linalool weighs 154? Well, what I've done is I take my molecule and I take an infrared of it first. And when I take my infrared and I see the OH in the spectrum, I then know that my mass spec is likely to have lost 18 mass units, so that I'm actually looking for a really small molecular ion that's lost 18 to form something that's a little bit more abundant. Okay, so alcohols can be a little tricky in their mass spec because they do like to lose water, and there's really nothing you can do about that. So that's one thing we have to be aware of. For alkenes, alkenes tend to break to form what are called allylic carbocations. Basically, an allylic carbocation is a carbocation that is sitting next to a double bond. That's an allylic carbocation. Those of you in Dr. Kwan's lecture, you talked about allylic radicals last semester. If you've been through the entire course, we talked about both in the entire course. But allylic carbocations tend to be more stable because they have different resonance structures. You could take this double bond and you could move it here and form then the other resonance structure for that allylic carbocation. And so the more resonance structures you can draw, the more stable the carbocation. So allylic carbocations with alkenes tend to be a fragment that you see a lot for those. And we did that in the first experiment. When I asked you to draw the remaining 6 carbocations for the triphenylmethanol, that's basically what you did, was draw those different resonance structures. So in this case, this one hexene weighs 84. And going from 84 to 69 is a loss of 15. That means that it broke off a methyl group. Only one place that it could have broken off a methyl group. So the 69 corresponds to all of this once the methyl group's gone. But notice that we now have a 56 and we have a 55. And then we have a 41, 42, and 43. The 56 is not just a C4. It's not just a C4 piece, because that C4 that's got totally saturated hydrogens weighs 57. So the 56 in this case would correspond to basically 1, 2, 3, 4. This 4-carbon chain would weigh 56, but with the carbocation, it's lost a hydrogen, and with the double bond, it's basically lost one more hydrogen. So it would weigh 56. This piece, if you think about, let's break this bond right here. to form the allylic carbocation. What would this allylic carbocation weigh? Well, this would be a C3H1, 2, 3, 4, 5. This would be a C3H5 piece. That would be 36 plus 5, which would be your 41, which is that. And you can see that the 41 and the 56 are the most abundant peaks because of the stability of that allylic carbocation. We're not going to try and predict what peak would be the highest, but we can sometimes rationalize, bless you, why one particular peak is higher than the others. Okay? And in this case, that carbocation is stable, which makes the 41 more likely. Everybody kind of see that? I'll take that as a yes. I'm not going to do that one. Now, when we get to benzene rings, and one of the peaks that is predominant with a benzene ring that has an alkyl group attached to it is the 91 peak. And the 91 peak comes from the benzylic carbocation being formed. So if you took, for instance, propylbenzene here, you would very easily cleave that bond to give you the benzylic carbocation. We already know the benzylic carbocations are stable because, again, if you go back to experiment number 1, I asked you to draw all those resonance structures of triphenylmethyl carbocation. What were they? They were all it was a benzylic carbocation. And so you can draw all the different resonance structures for the formation of that carbocation, which makes it stable. Now later on in the semester, when you get to talking about aromatic compounds in lecture, what you'll find is that the benzylic carbocation actually breaks open and forms this, which is called the tropylium ion. And the tropylium ion is also aromatic. And when we talk about aromaticity, or a molecule being aromatic in lecture, we're going to talk about that molecule being very stable. So the tropylium ion is actually what exists in the gas phase. But for our argument, we'll just say the benzylic carbocation. So last week I kind of showed you, well, if you do a search on a particular molecule in your compound, you'll get this whole list of potential possibilities. Well, I've usually looked at the mass spectrum, and if I see a peak of 91, it means somewhere in the molecule I got a benzene ring with an alkyl group on it. And so if I see that peak, it can help me narrow down my list, because I know I've got some sort of alkyl benzene in there. So that's a pretty easy peak to spot, and if you see it, that's what it corresponds to. Now, molecules with heteroatoms in them. And the heteroatom is either an oxygen, a nitrogen, a sulfur, could be a halogen. When you take those molecules and you form their radical carbocations, they tend to undergo what's called alpha cleavage. And alpha cleavage just means that they tend to cleave between the carbonyl carbon and an alkyl group. That's what's called alpha cleavage. Well, if we think about doing this and taking this molecule, which is pentano, if we think about cleaving that bond, what's going to remain? Well, of course I'm going to get an ethyl carbocation half the time, and my ethyl carbocation shows up at 29. But what about the other part of the molecule? What about this part? What about that carbocation? So in other words, if I cleave this bond, I'm going to get this, and I'm going to get my ethyl radical. Some of the time I'm going to get this radical and my ethyl carbocation. I can see that I've got my ethyl carbocation. Well, this heteroatom fragment has a resonance structure that you can draw. And so whenever you have a heteroatom next to a carbon with a positive charge, you can actually take the pair of electrons off of the oxygen or nitrogen and donate it here to form a second resonance structure that would look like this. Where you have a carbon-oxygen triple bond. This is actually what is called, these two together are called aselenium ions. And you'll talk about those when we talk about Friedel-Crafts acylation reactions. But again, the more resonance structures you can draw, the more stable the overall carbocation is. So the fact that I can draw two of these makes that fragment what we call resonance stabilized. And so that peak will show up predominantly in the mass spectrum. If you look at this of the 3-pentanone here, I mean, there's nothing exciting about this. You got your molecular ion, you got your 57 peak, which corresponds to that fragment with the 2 carbons, or sorry, with 3 carbons and an oxygen, and then you've got your 29 for the other decision the other way. So really, those are the only patterns that occur. And the reason they're the only ones that occur is simply because you get that resonance stabilized carbocation. Okay, so that's what happens with carbonyls. Now this can also happen with ethers. So if you look at this, this is basically 3-pentyl methyl ether. And if these two have the same structure, I just drew them slightly differently. But if I take my 3-pentyl methyl ether, it'll undergo alpha cleavage the same way. So the alpha cleavage will, in this case, occur at either this carbon or the other carbon. And when I cleave that molecule, I'm going to get my ethyl radical. Some of the time I'm going to get an ethyl carbocation. You can see I don't see much ethyl carbocation there. And then what's remaining looks like this. With that carbocation, and now I can draw the resonance hybrid of that by taking the lone pair off the oxygen and now moving it to the carbocation. And so I'll end up with now the double bond to the oxygen, and now the oxygen will have a positive charge. So that's a slightly different kind of resonance stabilized heteroatom. But in each case, when you have an oxygen or a nitrogen, the main cleavage is going to occur off of the carbon that's attached to that heteroatom, so that you can form one of those resonance stabilized carbocations. I'm almost done. If you have molecules that have more than one heteroatom, then you can kind of get the cleavage to be the same, alpha cleavage in both cases. This molecule, though, is interesting from this standpoint. This is the major cleavage point right there. And so sometimes I'm going to get the radical and the carbocation between these, but let's just say, for the sake of argument, let's write down the 2 carbocations that I would get. So if I cleave the bond and made this a carbocation, I'm going to get this species. And if I cleave the other one and form the carbocation, I'm going to get that one. Each one of these has the ability to form another resonance structure. So for this OH, I could move this pair of electrons here and then form the double bond and have the positive charge on the oxygen. Or over here, I can move the pair of electrons down here to form the double bond, and that would again put the positive charge on the oxygen. So both of these carbocations have 2 resonance structures. Now, which of those two is most likely to form? In other words, if I cleave this double bond, what am I going to see more of? Carbocation A or carbocation B? B? Everybody agree with that? So it worked really well on Tuesday afternoon was when I started asking questions and saying, well, when you answer them, then you get to start and leave. Then all of a sudden, everybody's hand went up. But it's B, why?
Resonance structure.
Each one has two resonance structures.
I think because the O is more electric. I mean, the O is like oxygen is electronegative, so we'll keep the electron closer on the A because there's less bonds.
So you think A is more stable? Hold on to the electronegativity idea, but not on this problem. If I just look at the two top resonance structures, if I asked you which one's more stable, just what would you think? B, but why? More carbons because it's a secondary carbocation, right? And I'm going to put that in quotes because it's not really, but really this one looks more like a secondary carbocation than this one that looks more like a primary carbocation. Now, you could look at it, you could look at the two bottom resonance structures and say, well, which one of these two is more stable? And you might be tempted to say that B is more stable, which it is. But why would you think that B is more stable than A with the double bond resonance structures? What makes a double bond more stable? It being more substituted, right? The more alkyl groups attached to a double bond, the more stable it is. That's what leads to Zaitsev's rule. So in this case, you would still say, you look at this and go, well, this has a methyl group off of it. It's going to be more stable than the one that just has two hydrogens. So you could look at either resonance structure and say that they both favor B. And that means that we're more likely to see in this spectrum a mass of, well, this is a C2, this is C2H. It's got, what, 3 carbons here, or 3 hydrogens, 4, 5, and an oxygen. So this is 24 plus 5 plus 16 gives me 45. Versus this one that's simply a CH3O. Because there's 2 hydrogens here, 3 carbon oxygen, which would be 12, 18, 21. So I don't even see the 21. Well, I don't see the 21 because it's not 21, it's 31. So what do I see more of? I see more 45 than 31. Why? Because the 45 carbocation is more stable. Right, so we can take the experimental data here from the mass spec and we can figure out which carbocation is more stable and rationalize it. Right. There's only 2 more, and this one I'm going to talk about in a little bit of depth, and then the other one we'll just kind of look at. Here's another heteroatom fragmentation. So I got a nitrogen and an oxygen. And I'm going to break that carbon-carbon bond. So here's my 2 possible carbocations. An NH2 with the plus charge and the plus charge with the OH. Okay, there's my 2 possibilities. Now, the peak on the left it's a CH4N fragment, and the peak on the right is a CH3O fragment. The CH4 would weigh 12 plus 14, 28. This one weighs 32, and this one would weigh then 31. We already figured out that was 31. So when the bond breaks, I can form either the 32 or the 31 carbocation. So which one do I form? What's the data tell me? The data tells me I form a 30. How do I get to 30? Let's see. Let's just figure out which one it is. Eli can figure out the math.
CH4 and 30.
CH4.
And 30. It's 30.
Okay. 14 and 12 is 26, not 28. You might need a calculator when you figure these masses out. Okay. So there we go. 30 versus 31. Which one is more stable? Data tells us I see a ton of 30, I don't see much 31. So the data says that 30 is more stable. Let's just draw the two resonance structures and see if we can explain why that's the case. So if I bring this pair of electrons down here, I would have a double bond with my NH2 plus, and then over here I would have take my pair of electrons there to form my double bond with my OH plus. Okay, so there's my two different resonance structures. The fact that I see 30 in the mass spectrum tells me the nitrogen-based one is more stable. Can anybody propose why it's more stable than the oxygen-based one? Electronegativity of nitrogen versus oxygen. It's less, true. Nitrogen is less electronegative. How does that play into resonance structure on the left being more stable than the one on the right?
Be more likely to have a positive charge.
Well, it's able to better handle the positive charge. In determining resonance structure stability, there are three things that go into comparing resonance structures. Number one, do all the atoms have completed octets? If the answer is yes for one and no for another, the one that has completed octets is more stable. Now in this case, the carbons don't have completed well, they do have completed octets, I suppose, but in the carbocation part, they don't. But then in the other one, I suppose they do. But the oxygen doesn't. So we can't actually form completed octets for all the atoms in this structure. So they're a tie. So next we go to charges. Does one structure have more formal charges or higher formal charges than the other? Well, in this case, they both have plus ones. That's a tie. If one was plus 2 and the other was plus 1, the plus 1 would be more stable. Okay, then we go to the third tiebreaker, which is electronegativity. Does the charge make sense with the electronegativities of the atoms? Okay, in other words, which atom, nitrogen or oxygen, is better able to handle a positive charge? Well, the one that's able to handle the better the positive charge is going to be the one that's less electronegative. So in this case, nitrogen is more able to handle a positive charge than the more electronegative oxygen. And so then that makes this resonance structure more stable. So in this case, it's more stable, and if it's more stable, then what do I see? I see more 30 than 31. Okay. Now, in past years, I haven't gone through fragmentation like very much. But I think what it does help us do is it gives us an opportunity to practice drawing resonance structures, and it kind of sets up benzylic carbocations and also these types of aselenium or alpha cleavage type carbocations that you're going to see in lecture later on. And now what I'm going to do is I'm going to give you some mass spectra, and I'm going to ask you to tell me what peak, what the structure, what carbocation corresponds to what peak in the spectrum. And then if it has more than one resonance structure, I'm going to ask you to write more than one resonance structure. So I haven't written it yet, but I will sometime between now and the end of the day. When I do that, I'm going to pretty much mimic what I've talked about here. So in other words, if you go back and you look at what we did here, you should be able to answer those problems. So it's not going to be anything taxing, although it may seem so. So that's how we can deal with, if you have different heteroatoms, you're going to have different stabilities of the carbocations. And then the last thing that's probably the most important of the cleavage patterns is what's called McLafferty rearrangement. And basically, we'll talk more about McLafferty rearrangements later on. But if you have a carbonyl, and your carbonyl has an alkyl group that's long enough to be able to put itself in this six-membered ring or get itself to where it can form a six-membered ring transition state, what it ends up doing is it ends up cleaving, and in this case it cleaves along this bond. So that bond breaks, the arrows move the way that they're shown, and we end up forming a neutral alkene, and we end up forming what's called an enol radical cation. Now, that enol undergoes what's called tautomerism, and we'll talk about this. You'll talk about this first when we talk about alkyne reactions. This enol undergoes an equilibrium called tautomerism to form then basically its ketone version. And tautomerism basically means that is the simultaneous movement of electrons and a hydrogen atom. Okay, so in this case, going from having this OH group here, what happens is this pair of electrons moves here, then this pair of electrons comes down here, and the hydrogen moves to that position, and the carbonyl forms. Okay. Those two are not resonance structures, despite the fact that that's the arrow that I've used, which is incorrect. This should be one arrow this way and one arrow that way. And so later on, you'll find out that those enols tend to be really unstable, and they tend to form ketones right off the bat. In the mass spec, it doesn't matter because actually enols are okay and they have the same mass. So you can get this McLafferty rearrangement to split the molecule up, and then you'll see the fragments that correspond to that. I'm not going to ask you to do one of those in the homeworks, but it is the most famous of the rearrangements. We'll talk about that later on. Okay, so what I'm going to do then, as I said, is I'll give you a mass spec. I'll give you some mass spec. I'll ask you to write out how the molecule cleaves and what fragment it corresponds to, and all the fragments have to be carbocations. Okay, they can't be radicals because radicals don't have a charge; they don't move in the mass spectrum. You can't determine their masses. Okay.